So like I said, your exam is going to be Thursday here, September 10th. Remember, you're taking it online. You'll be taking it in Canvas when you're logged into Canvas. And you will see a module opening up that it's pretty clear. It says Exam 1 module. You will just open it up in there. It's going to have you take it using the Respondus monitor system, that system we talked about already. I'm looking at it right about now. So yeah, that module will open up. It'll be pretty clear. You have an allotment of time to work on the problems. You have, let's see, I give you 90 minutes. That should be more than generous. What you'll do is, while working on the exam, you will want to take good notes, good scratch work, and make sure your numbers are ordered, your values, everything, the problems are in order, everything's neat and clear. Don't send in a bunch of scribbly scratch, or I can't help you out with that. The whole point of it is to give you some points back on your exam for scratch work. That is my ultimate goal. So definitely make sure it's as neat and clean as you can. So yeah, you'll see that open up in Canvas. It's pretty straightforward. And then the first time you ever try to take it, it's going to have you download the Respondus Monitor Lockdown browser. And then whenever you get that browser installed, it's pretty straightforward. It'll connect to your webcam that you're using, and it will monitor you during the exam. It covers everything up to and including section 6.1. If you look under the assignments, 6.1, so those are all the homework sections available to you. You can study for the exam by working the open homeworks, the ones that are not due till September 10th. You can work those. Remember, it's risk-free to work on homework in MyLabs. Plus, you can work a problem as many times as you fancy until you get it right and get credit for it. Past due assignments that are no longer open, well, if you click the grade book in MyLabs Plus, you can actually still go into those past due assignments and you can work the problems in them. They'll give you new numbers, they'll give you fresh stuff. It's great extra practice. It won't actually improve your grade because it's already past due, but you can do that for some additional practice and help on the upcoming exam. So I think everything is set up properly, and we can go ahead and move forward. So we have been looking at linear equations in one variable, We will review briefly. Remember, a linear equation in one variable is one that can be written as some number times x plus some other number equals 0. It could also be subtraction. If you can rearrange an equation in any way to look like that, it's a one variable linear equation. One variable because only x is the variable. A and b are going to be actual numbers plugged in there. And we talked about how you actually solve some of these equations. You can move things over to the other side. You can add a number to both sides, subtract numbers from both sides. The goal is to isolate x. So first get x by itself with its coefficient, the number in front of it. And then whenever you're ready, you can get rid of the coefficient either by dividing both sides by a number or multiplying both sides by a number, whatever makes sense so that you get x by itself. So the ultimate steps to this: simplify the algebraic expression on each side by removing grouping symbols and combining like terms. So get rid of parentheses. If you need to distribute something or whatever it takes to drop parentheses, that's what you need to do first, because parentheses keep things from being on the same playing field. That's how I like to describe it. It keeps things from being together, so we need to drop those parentheses, however that needs to happen. What you want to do is get the variable on one side of the equation, completely on one side, and then everything else, move it on over to the other side. Then you're going to want to isolate the variable and solve. If you need to move the numbers over that don't have the variable attached to it, do that. Get the variable by itself. So we kind of worked some of these problems at the tail end of last class. We did a little bit of this stuff here. So if we were looking at this specific problem here, 2 times in parentheses x minus 4, outside the parentheses minus 5x equals negative 5. Well, we'd want to distribute this 2 here because these parentheses keep everything from being on the same playing field. They're no longer on the same playing field, and that is important to us. We need them all together. So the first thing we do is we distribute this 2, and we end up with this business here, 2x minus 8. But then we still have that minus 5x equals negative 5. So we need to combine those like terms. The 2x minus 5x becomes negative 3x. Then we have negative 3x minus 8 equals negative 5. So the variable is on the left-hand side of the equation, which is where we like it. But this 8 is plaguing it at the moment. So you're going to have to add the 8 over to the other side. We need to add 8 to both sides. So the left-hand side just becomes the negative 3x. The right-hand side, negative 5 plus 8, becomes positive 3. Now the only thing plaguing the variable is the negative 3 coefficient. So we can divide both sides by negative 3. Bada bing, bada boom, you're going to get negative 1. You'll get negative 1 by itself, and that's our answer, x equals negative 1. You can check and make sure an x value of negative 1 is going to work by going all the way back to the original equation you started with, plugging a negative 1 in for x via function evaluation that we've talked about before. Let me grab a swig of water here, and if you get a true statement out of that, it worked. So you plug in negative 1, you do the math, and you come down with the statement negative 5 equals negative 5. That's a true statement, so you know that your solution worked. You know it'll work. So the only solution is negative 1. That's actually kind of an interesting thing. The only solution is negative 1. It turns out if you have a one variable linear equation, no other kind of equation necessarily does this, but a one variable linear equation, hey, guess what? You're going to have exactly one possible solution, no more and no less. And that's actually really interesting. So once we know we've found x equals negative 1 as a solution, we happen to know that it is the only solution, simply by a rule of how linear functions work. So we can look at some linear equations. I'm not horribly concerned with this right now because this is graphing it. One thing I'll mention is that you have a linear equation here, 10/9 x plus 53 over 9 and 1/9 x plus 26 over 9. You see these equations. Well, what we're going to see is that the value in front of the x, when it's written properly like this, the value in front of the x is called the slope. And we think of slope as rise over run. So every 9 units we go over to the right, a slope of 10/9 would go up 10 units. Over here, rise over run is 1 over 9. So for this one, every 9 units we go to the right, the thing only goes up 1. So that's why this line here, the high humor group, whatever that is, this high humor group, that's why the slope of this line is much milder. It's not as steep, whereas this one has a greater slope, so it is much steeper. But we'll go into detail later on in the semester of exactly what these mean here, what these values mean, the slope and y-intercept. So you can do some mathemagic with it. You can do a little magique. Now let's look at a few interesting ones. And I'm going to go on and do my own thing on this one because I likes the way I teach it better. Let's go to the whiteboard. There's going to actually be a few interesting cases where you're going to find a linear equation, you're solving it, you're going to find no solution. So you're like, Josh, you said every linear equation has exactly one solution. Okay, but there's a big but, B-U-T, but, attached with it. The linear equation does technically have to behave a certain way. That behavior it's going to be fine if you've written it in the standard form of ax plus b equals 0, you're fine. But if you try to write a linear equation, what you'll see is that when you do some of the manipulations on it, if it makes a mistake or makes a problem, then you'll know it actually wasn't truly a linear equation. What am I talking about? I'm just babbling? No, let me show you. Let's solveify. Let's make an interesting one. 14 minus 3x plus 6x equals 7 plus 3 times 2 plus x. Let me write that a little better. And you'll see what I mean in just a moment here. All right, well, we got to start doing some of the heavy lifting on that. We'll take a swig. I tell you what, nothing beats good old-fashioned water when it comes to satisfying your thirst. I can tell you that. So, why are you talking about water? This is a math class. Will, I likes to have fun, folks. So, we want to solve this. The first thing we see is that we've got some parentheses, so that means everything's not on level playing field. So we want to start by distributing that 3. And then on the left-hand side, we notice we could combine like terms. And yeah, if we got to group all the things with variables on the left-hand side and then combine like terms, we can do it at any stage we want. So I'm going to combine these like terms here. Well, what that's going to give me is 14. That didn't have anything special with it yet. I have minus 3x plus 6x. If I add negative 3 plus 6, I'm left with positive 3 of that thing. So it becomes 14 plus 3x equals. Now I will go ahead and I will distribute out the right-hand side. The 7 is just there. It doesn't have anything with it yet. I distribute that 3. I'm going to get plus 6 plus 3x. So you'll notice, ooh, something's rotten in the state of Denmark, which is a reference to the play Hamlet. Great play, classic. There's a 3x over here, positive 3x. There's a positive 3x over here. So before we see what's about to happen, you're going to notice that no matter what I plugged in for x, the left-hand side and the right-hand side are going to balance each other out perfectly. And that actually creates not a bad thing per se, just something that we have to understand what's going on. But what I would normally do, so first thing we can do this 7 plus 6 here. That's not a big deal. 13 plus 3x on the right. On the left, we didn't do anything, just still 14 plus 3x. Now, what we want to do is we want to get everything with x, and let me write this a little bit better. I don't like how sloppy my handwriting is sometimes. I'm sure you guys are not fans of it either. We want to get everything x on the left-hand side if we can. So what we got to do then, we got to move this 3x over. But wait just a minute. Normally, this wouldn't happen. We don't want it to happen that way. But it just so happens in this problem, if I move the 3x over, I'm actually getting rid of x. X is gone. And I'm left with the equation 14 equals 13. The 3x's are gone. There is no x left in this equation. What that means is even all the way back in the original equation, x could have just been eliminated through proper mathematical channels. So x never really had any influence on the equation. Not really, because no matter what, it would have done the same thing to both sides. It doesn't actually influence the balance of the equation. And let's just use common sense. Everybody in the text box, tell me, does 14 equal 13? Does 14 equal 13? Xavier says no. Everybody else, what do you guys think? Is 14 equal to 13? It's not a trick question at all. Don't you love it when you're in a math class and I don't ask a trick question? Yeah, it's straightforward. This is nonsense. This is a clearly false statement. That is nonsense. It's out the door. What this means, I'll write this out in text as well. What this means is that no value of x is certainly gone here, but even if we went all the way back up here, no value of x could have remedied this bad situation. Now you can't tell it's a bad situation from the beginning. You have to see it when you come all the way down here. But no matter what value of x I plug in here, I can never make a true statement out of this equation, all the way back to the original. No value of x produces a true statement out of the original equation. And that's the whole point of solving an equation. You want x values or values of your variables, you can plug in and just create a true statement. But you can't do it here. It's not going to happen. What this means then is that there's no solution. There is no solution. The solution's not x equals 0. X equals 0 doesn't even work. There's no solution at all. Nothing works. There's no number you can pick. We can sometimes symbolize that with something called the empty set. It looks like a 0 with a line crossed through it, Ghostbusters symbol almost. Maybe I should draw a ghost coming out of there. And if you like Ghostbusters 2, the ghost is coming out and it has a 2 sign on its hand. Anyways, yeah, this is called the empty set. There's no solution. This is literally the answer. And that's not the number 0. That is the set containing nothing. So yeah, that's one of our interesting statements. You do some math, you see something fishing going on, and you end up with a false statement, and you've eliminated your variable, get out of here. Now, if this was 14x equals 13, that's fine. The variable has not been eliminated, which means there is something you could plug in for the variable to make that into a true statement. So if your variable doesn't get eliminated, you're okay. But if your variable does get eliminated like it really did, that's a problem. So in this case, we created a situation where there was no solution. Now, let's look at the case where we have the opposite problem. Let's look at the case where we're actually going to accidentally create too many solutions, an infinite number of solutions. And it's funny because I can write out an equation that looks tricky and it looks weird and it looks complicated, but then it comes out to a pretty simple idea. So I'm going to have to engineer this one carefully. I don't like the one I have in my notes. Let's make it more interesting than that. Let's make it even more interesting than that. I gotta do a little quick mental math on the fly here in order to engineer a good problem. How about that? And hopefully I have created a good thing here. So we've got this equation. Again, our goal is to solve it. In the last one, we attempted to solve it, but there was no solution. But that's still the right answer, is to say no solution. We didn't break any rules. Now, in this particular case, the problem we're going to have is we're going to still eliminate the variable, but something else that's wonderful is going to happen. So it looks bad, but let's go about simplifying it. We need to drop out parentheses. We need to get rid of them, get everything on the same playing field. So we need to distribute this 4. We need to distribute this 7 over here. We'll combine like terms. Then we'll work on getting the variable onto the same side of the equation, everything else on the other side. Bada bing, bada boom. So let's see. We distribute this 4. We're going to get 4x minus 24. This plus 17 was already there, so it just stays. Equals, we distribute the 7. We're going to get 14x minus 7 minus 10x. Well, all right then. Let's combine like terms on the left-hand side. 4x doesn't have anything. It's all alone in this world. So what we're going to have to do is wipe my face real quick. Only the constants here combine. So the 4x stays in the playing field. Negative 24 plus 17, I can tell it's going to end up being negative. Once I know it's negative, you can actually flip them on their head and say it's 24 minus 17, which is normally, or is, 7, but then it just happens to be negative 7. And then what we'll say is that equals, well, 14x minus 10x, which is just going to be, okay, that reduces to 4x. Uh-oh, something fishy's going on. And then that minus 7 didn't have anything. Uh-oh, something extra fishy's going on. What in the heck? Now, I might just have to say a swear word here, and please don't report me to anyone. What in the gosh darn heck is going on here? I'm sorry if that offended anyone, but oh, I'm real passionate about this. No, but look, we got the same thing on the left and the right-hand side. So if I plug in a 3 for x, I would do it here, and I would do it here, and whatever the left-hand side came out to, the right-hand side would also come out to. That means 3 is a solution to this equation because a solution is simply a value that can be substituted in for the variable that makes a true statement. So 3 works for x. What about 4? Sure, I can plug a 4 in for x. What about 5? Yeah. 6? Yeah. Ugly numbers, 2.789462. Sure, I plug it in here, the same thing's going to come out on the right-hand side. Negative numbers, 0. You plug in 0 for x, it works as well. The whole point, no matter what x value you pick, if you plug it into this equation, you're going to get a true statement out of it. That means that x, the solution for x, earlier the problem was there was nothing that worked. Now the problem is everything works, all real numbers. And so there is a solution, but it's just not interesting to say that any number could work. It's not discriminating enough. We like it to be a little bit more selective. So if you don't believe me or you would like to see what happens, we'll just continue to try and solve the equation like you normally would. You'll need that. Does that mean x equals x? Kind of. That is basically just, I mean, even x equals x would be an equivalent equation here. What that means is that if we continue on like we were solving it, we'll just end up with the statement negative 7 equals negative 7. This is said to be, it's the same thing on both sides, but we've eliminated our variable. But got a true statement. Earlier, we eliminated the variable and we got a false statement out of it. 14 equals 13 was false. Here, we've eliminated our variable, but we've gotten a true statement out of it. What this means then is that the variable has no influence on this equation in terms of making it wrong or right. The equation was always going to be true no matter what x value you want. So we could have picked any value for x and gotten a true statement. This means all real numbers work. The solution set is all real numbers. The solution set is all real numbers. We used that fancy symbol earlier for the empty set. Now we can use this one. Remember we said the real numbers use that fancy R. So that fancy R is really the solution. It means any number you want. It's like Charlie and the Chocolate Factory. You can have any piece of candy you want. And that just goes to show how old I am. I remember that movie. Okay, so let's see what we're going to do here. That finishes up section 6.2. I say we get a start on the next section just a little bit. And yes, it's not going to be on your homework, but, or excuse me, on your exam. But as they say, sometimes it's just what do you got to do about it is what you got to do. we'll get a start on it just because it is kind of interesting. But then what we'll do is after that we'll take our break, and then we will do a review for the exam after our break. So let's open this up. Give me uno momente, por favor. This thing has decided to be slow today. It says, Josh, we will not allow you to go fast today. That's not going to happen. And I say, will you please speed up anyways? And it says no. Okay, here we go. We're starting to get it. Let's actually do this. Let's hold off on the next section just because there's no point in getting that far ahead. Let's talk a little bit about proportions. This will kind of be a clear all. Let's talk about percents, because percents are really super duper important, really in all of mathematics. We're going to be revisiting the concept of a percent like 100 million times throughout the rest of the semester. So a percent, what it does is it expresses something out of 100. There's 100%, literally the word per cent. Cent it's Roman, so I guess Italian, and it means 100. Cent is 100 of something. A century is 100 years. There's 100 cents in a dollar. Per cent then means per 100 units of something. We use percents just all the gosh darn time. It's very important that we have a basic idea of percent. So what we do is we can convert between decimal and percent forms. 1 second. So we can convert between decimal and percent forms by multiplying or dividing by 100. But I like to think of it in a little bit of a different way. So let's say you had the number 0.03. Well, just regular numbers are out of 1, not 100. So we'd say 0.03 over 1. So when I say out of or per 1, I can literally think of the word division. The word per makes me think of division. Percents being out of 100, well, if I wanted to show the equivalent thing, then I would need to multiply the top and bottom by 100. And that means I'd multiply the top by 100. That gives me 3 on top. So 0.03 is equal to 3% per every 100 units. That's a pretty bad percent sign, but you get the idea. Maybe I'll use a text box. 3%. And that's really the justification behind it. So long story short, we can move down the line here. We'll put a line in the middle. And we'll say converting from percent to, or let's say decimal to percent. Decimal form to percent. What are you going to do? You're going to multiply by 100. Which also means you can move the decimal point to the right 2 spaces. So for example, we start with decimal form. Decimal form is the way you've always known numbers, just not written as fractions or anything, written as actual decimals. So decimal form, what's an example? Well, let's say you started off with, we did 0.03 a second ago. Let's say you started off with 0.65. Well, that's like 0.65 out of 100, or excuse me, out of 1. And what you'll see is that converts into 65%. We multiply it by 100, so the decimal goes there now. And so you can say that's 65.0%. Heck, you can even get rid of the 0.0. You don't even need it in there. You can just say it's 65%, because the decimal, when it's all the way to the right of the number, the decimal is not necessary to write, to put down. So I can literally say that 0.65 is equal to 65%. In fact, they're really the same number. They're the exact same number. They're just different expressions of the same idea, that I'm taking 65% of something. And 65% is a little more than half, not quite 3/4, right, of something. So you can do that. You can do that. We did 0.03 earlier. What about even smaller than 0.03? What about 0.000496? Don't let it fool you. You're just, if you know you're starting with a decimal and you need to convert to a percent, go 1, 2 spaces to the right. And then what you're going to get, let me just move this over a tad. What you're going to get then is still going to have zeros in front of it, 0.0496%. Huh? Isn't that cool or what? I think it is. So this 0 here before the decimal point is just, you can have left it off. You could have said it's just 0.0496%. It's just kind of what's your flavor. I know a lot of students in recent years told me they like having that 0 there, so it really makes it clear where the decimal point is. But it isn't necessary, per se. You can also have a number like, say you have 49 point, let's not do 49, let's make it more interesting than that. How about 59.63? If you're starting with 59.63, you're tempted to say, well, that's already a percent, all right. But that's not necessarily true. If you happen to know, you just have to know your context. If you happen to know this is already supposed to be in decimal form, then, and you know you got to convert to percent, well, you still got to move the decimal 2 places to the right, and that's going to leave you with 5,963%. And you say, Josh, 5,963%? I thought percents had to be between 0 and 100. And that actually just depends on the context of what you're talking about. If you're talking about parts of a whole, like you're splitting up an inheritance that's worth $2 million, yeah, if each person gets 20%, all the percents have to add up to 100%. You can't go over 100% because that means you would have really had more than 2 million. But if you would have had more than 2 million, then whatever the real amount is would have been the whole pie. So yeah, if you're talking about parts of a whole or a pie chart or something, yeah, it has to add up to 100%. But percents in general can express a lot of things. They can express growth rates. So if you have $100 in your, or if you just have $1 in your bank account and it grows by 100%, that's like saying it doubles to $2. But if it grows by 5,963%, it actually would grow by $59.63. So it just depends on what you have. That's really all it is. It just depends on context. You can have percents that are greater than 100%, just depending on what you're dealing with. Now let's say you're going the other way. Let's say you're starting from a percent and you want to go back to decimal form. Well, that's okay. So converting from a percent to decimal form. Well, earlier you multiplied by 100. The opposite of multiplication, you're going to need to divide by 100. And secretly that means move the decimal point to the left 2 spaces. So you need to know that you're starting with a percent and trying to move it back to a decimal form. So for instance, if you started with 42.1%, you know you're starting with a percent. If I didn't put the percent sign, that's just the number 42.1, which is in decimal form. So it's proper that if you know you're supposed to be talking about a percent, you put this percent sign. And let me write it properly. So if you know you're starting with a percent sign and you want to translate it back to a decimal, you would need to move the decimal point 2 places to the left. Uno, dos. So it would be 0.42 as a decimal. And sometimes you like to throw that 0 there before the decimal point to make it just really darn abundantly clear where the decimal point is. Sometimes it's easy to gloss over the decimal point if you don't put that 0 there. So a few other examples of this. Let's say you were already starting with a very small number. You're already starting with like 0.0456%. Just because it looks small, you naturally just want to move the decimal point to the right 2 spaces. Don't let it fool you. If you know you're starting from a percent and you're trying to go to a decimal, you need to move it to the left, whether you like it or not. So you're going to go 1, 2 spaces to the left, and you're actually going to have a really, really, really tiny decimal number, 0.000456. But that's just the way the game of baseball goes. That's just how it is in life. So don't let that trip you up. And then finally, those are kind of all the interesting examples. But if you had the number 6,110,457%, okay. The decimal point's not written there, but if it's not, it's implied to be right here. It's implied to be right there if you don't see a decimal point. So you're going to move it 2 places to the left in order to convert it into a decimal number. So it'll be this number, and then you put a comma here if you want, 61,104.57. Now that is just cool. Everyone say to yourself, that's cool. You know what? Let's go the extra mile. I want everyone to write in the text box, that's cool. Go ahead. That's cool. Thank you. Thank you. 2, we got 2 people saying that's cool. Let's get a couple more people saying that's cool, huh? For my benefit, and it'll make me happy. Very nice. A man who does not follow with the quotidian with the rest of the crowd. Very good. Yes, that is cool. Thank you very much. All thank you. So we know now we can convert between a decimal form and percent. But there's one other tricky form. We can have fractions. We can deal with fractions. And remember, fractions can be converted to decimal form. And then you can go even one step beyond that and convert them into percent form. So let's look at the fraction. Let's just say fractions, decimals, percents. That's going to be kind of our focus here in this part. Really the best thing to do is lead by example. Now we already looked at how to convert a fraction into a decimal. For instance, if you have the fraction 3/4. What you're literally saying is you're dividing 4 into 3. You might say, Josh, well, 4 doesn't go into 3. Well, it can if you expand your mind, if you give yourself a decimal point. And then remember, we can give ourselves as many zeros as we want over here in order to figure out what is the pattern, if there is a pattern that's just repeating, or If there is a terminating point, we just need to keep going until we find it. So now instead of saying we're dividing 4 into 3, we can say we're dividing 4 into 30. It goes in 7 times, so long division. And now there's a 2 down here. I can give myself another 0. And 4 goes into 25 times. And it does so cleanly, so we don't need to keep going. We can say there's no remainder. And then if you want, you can put that implied 0 there. It's not going to affect anything. So you might have already known that 3/4 is equal to 0.75. But then 0.75 rather, is equal to 75%. Move the decimal place point 2 places to the right. You got 75%. So by proxy, that means just straight up 3/4 is equal to 75%. And yeah, it's also equal to 0.75. That was a middleman, but this is also a true statement. So that's pretty cool. The nice thing is say you're on an exam or something like that, the numbers, because you're not allowed to use a calculator, the numbers have to kind of behave. They have to behave in a pleasant manner that wouldn't require you to have a calculator. So for example, I'm not going to ask you to convert, let's do something nasty, like this thing. I'm not going to ask you to convert that fraction into a percent. Get out of here. I wouldn't do it by hand. That's ridiculous. You got to divide 6,229,890. There's no 6,229,891,457 into 300. Get out of here. I'm not even going to do that by hand. I'm going to go pop that into a calculator. So that brings us to a good point. Let's say you were using a calculator. Let's peer ahead. All you got to do is take your calculator and let it do the division. You're clearly just going to have to round at some point. At some point, you're just going to have to decide, okay, these decimals go on forever. So I'm going to do 310,456 divided by 6,229,891,457. If you write it as a decimal, and remember when you do the calculator, it's automatically going to give you the decimal form. There's 3 zeros, then 4, 9, 8, 3, and then it looks like 3's repeat on forever. So whatever, we'll just write it all out. And then the 3's actually go on. So if I wanted to convert that to a percent, 1, 2. And now it's going to be like this. So I'm not going to ask one of these types of problems on the exam because you're not allowed to use a calculator. But just don't forget that division can be done in the calculator, but we have to wean ourselves off of that. The calculator is more of a crutch than you would believe. Besides, don't you want to have special skills that a calculator or a computer can't just do for you? Don't you like knowing that you have a job and that the world needs your skills and that whatever skills you're gaining can't just be done by a computer? Well, yeah, I mean, automation is destroying lots of industries. Computers being able to do work that human beings previously had to. It's destroying a lot of industries, and it can destroy even more industries than you think. Did you know that there are computers that will produce art? I mean, art, like pictures, drawings, paintings. There's an AI, an artist set up an AI that would control this little robot thing. It looked like a robot that would do paintings, and it could pick its different painting styles. It would use a spray can. It had a camera set up so it could see its own painting to make sure things were coming out. And that painting turned around and was put out on an art exhibit, and no one was told that an AI did it, and people were asked about their opinions. And they, it's the art community, so everyone, just, the artist used whatever, and he used this kind of shading, and, nobody knew it was an AI doing that. And that's scary because it didn't just look like a bunch of weird zeros and ones like in cliche science fiction movies. It was actually, it fooled real art snobs who are supposed to know when something's done by a real artist and when something's fake. So that is scary if art can be reproduced, because art is subjective, right? a computer is not supposed to have the ability to do that, but it does. So put another way, you need to learn some things without using a calculator. You know, what's the point? Don't you want to have some special skills and knowledge? I think we all kind of should focus on that. So anyways, you can start with a fraction and you can turn it into a decimal because a fraction is just one number divided by another. So do the division. You can then take the decimal and turn it into a percent. Vice versa, you can start with a percent and you can turn it into a fraction. Now you can do it a couple ways. You can start with the percent, convert it to a decimal, and then we talked about how you go from decimals to fractions. That's, you know, whatever you want. You can also start with, say you had the percent 68%. Well, the cool thing is 68%, you could argue that that's equal to 0.68. You move the decimal 2 places to the left, and you're not wrong. But another way to think about 68%, you could go straight up and say, well, a percent is whatever the number here is, the 68, out of 100 per 100. So that's just equal to 68 over 100. And oh my goodness, you already just turned it into a fraction. You just turned 68% into a fraction. That's great. And then you can simplify it. It looks like both the top and bottom could be divided by 2. So you'll get a 50 on bottom. 68 divided by 2 is 34. You can keep going with that. Top and bottom can be divided by 2 again, and you can get 17 over 25. And then it looks like that's in simplest form. So 68% is the exact same as the fraction 17 over 25. Now you could have done the same thing if you had decided to convert to a decimal first. Doesn't really matter. And you remember our method for dealing with decimals is we say, okay, however many decimal points you go out to. So you went out to 2 decimal points here. Cool. That means take this number and put it out of 100. Take the 68 and put it out of 100. Oh, but then you would have simplified it all the same into 17 over 25. So if you're dealing with a percent and you want to move it into a fraction, you don't necessarily have to convert it to a decimal first, but you can. You're certainly welcome to if that kind of floats your boat there. Let me see. Let me find a few more kind of interesting examples of this real quick. Let me see if I can find one that's just cooler. Something not in my notes. I like going off the notes. The notes they're okay, but I like kind of going off the beaten path a little bit. I'm a rebel, you know. I'm a free spirit. Blah blah blah. We actually covered proportions to a reasonable degree. Boy, MyLabs+ is going slow right now. So yeah, the last thing I guess we can cover for percents at this moment, this juncture, how do you take a percent of something? So earlier we said, hey, what if you have that the $2 million inheritance, and a person passes away, and they leave $2 million for their kids, and he has or she has 5 kids, so they'd each get 20%, which is 1/5 of the inheritance. How do you actually take that percent? Well, there's a couple ways you can do it. You can first convert the percent into a fraction, and then you can just multiply your fraction by the whole, whatever the full amount is, and do it that way. Or you can leave it as a percent and just go straight up with it. So here's the truth. Let me give you guys some truth. I hope you're ready for this. It's going to shock and appall. Truth. A percent is just a kind of a tool for us to make sense of numbers. Look, when you talk about half of something, when you're saying, okay, we got half of this, it's just easier to call it 50% than it is to say 0.5, although they're the exact same thing. It's easier to say, okay, 50% of this money is going here. it's easier just to say 50% than 0.5. 50%, it's like we can cut it into 100 things and tell me how many of that 100 go towards this goal or whatever. So percents are simply a kind of a shorthand way or a common way of expressing a number or a value that you can express it verbally. You can say it to people and it makes sense. But the true number is 0.5. That's what the number really is. 50% is just a convenient way of expressing that same number. So how do I take a percent of something? I'm going to use something called the percent equation. The percent equation. The percent equation is A equals P times B. Where A is the part of the whole that you're talking about. P is the percent, but here's where it's confusing. It's the percent, but expressed in decimal form, which is why it's confusing. That's why I went over this over here. And then B is the whole amount that you're taking a slice of, that you're taking a piece out of. The way you can read it is A is P percent of B. In math, the word is should make you think of equality. The word of, believe it or not, it's not told to you this way, but the word of should make you think of multiplication. So the word is, does that? Of makes you think of multiplication. So A is equals P percent of multiplication B. So if it asks, what is 20% of $2 million? Well, how many of you out there would love to have 20% of $2 million? Even if it's not the whole pie, yeah, I'm not going to turn down 20% of $2 million. And the reason is that the most important thing in life, the thing that everyone ought to strive for, is to be rich. All right, it's to have a lot of money, because money is the most important thing ever. That's not true, but that is the joke I like to make. Hopefully I did not offend you. I don't really believe it. So we look at our percent equation. We need an A, we need a P, and we need a B. A is actually what we're looking for here. It's what we don't know. P is the percent. Now we would say it's 20%, but remember we need to write that as the decimal 0.2. Because when we actually do the math, we need to use the number 0.2. 20% is just a nice little verbal way, or a little way we talk about things, a slang term for 0.2. And then B is going to be the 2 million. You don't have to put the dollar sign with it at the moment. So what we don't know, we'll leave it as a variable in our equation. So A, we don't know, is equal to 20%, or 0.2 times 2 million. Now you can do that freehand. We'll talk more specifically how you multiply decimal numbers with whole numbers, the little tricks you can use. But you can just kind of skip to the point, and we'll say it's 400,000. And that's how we take a percent. You want 20% of 2 million, take 0.2, multiply it by 2 million, you get 400 grand. So if each person gets 20% of a $2 million inheritance, that means each person gets $400,000. Not a bad amount of money to get. You can go buy a house with that and not have to worry about house payments. Though you still got to pay property tax. You still have to pay property tax. Haha. You have to do it no matter what. They get you that way. Okay, let's go ahead and take our break, about 15, 20-minute break here, give or take. We'll come back around 146, 147. And we'll take our break, and then we'll spend the second half after the break just reviewing for your first exam. So everyone say, all right, Josh, that sounds like a great plan. Okay, so we have 4 principal operations. So we'll talk about negative numbers. There's 4 principal operations, so let's divide the whiteboard into 4 parts, rough parts here. Addition, subtraction, multiplication, and division. Now addition, you always want to think about a number line. Also, remember addition and subtraction are secretly, they're the same thing. So here's what I'm actually going to do. Tricked you. We're going to put them together. We're going to lump them together. And one second. And then multiplication and division are secretly the same thing. So what we can do with those, we can make a number line. That's always what you want to think about when you're doing these. Number line. So say you had, I don't know, let's start with negative 14 plus 7. What that says is you're starting on the number line at negative 14, and you're moving 7 spaces to the right. Now you can tell you would need to go 14 total spaces before you could get back to 0. So going 7 spaces to the right is not going to get you far enough there. So it's going to be a negative number no matter what. You're still going to be on the negative side of things. Once you know that, there's a couple things you can do. You know it'll be negative, but then what you really do is you say, okay, it's negative, but it's getting closer to 0. So it's going to be somewhere in here. And you could almost think about it in a way as doing like 14 minus 7. You're taking 7 spaces away from how far you are from 0. But then you know it has to be negative. So it ends up being negative 7. And so it kind of operates in a little bit of a method like that. Addition, if you're adding a positive number, you think about moving to the right. But if you're adding a negative number, let's say you start with a negative number, negative 5, and you add to it negative 6. Let's just call it like it is. Adding negative just turns it into subtraction. So it's negative 5 to start with, and then you're subtracting 6 from it. So think about the number line. You start at negative 5. If you're taking 6 away, that's moving it to the left. So you're going 6 units to the left. So it's only going to be even more negative. So you know that the answer to that will be negative. And then you can almost think about it as like 5 plus 6, because it's like you're taking 5 units away on the left of 0 and going 6 more units that way. So it ends up being negative 11. Now, that's kind of going to be useful to think about it, addition, subtraction. The negative numbers make it kind of a pain, but you just got to remember, where are you on the number line? Which direction do you need to go? And is it going to make you go positive, negative? You can also do this. Let's say you had negative 10 and you were adding 18 onto it. There's a couple things you can do with that one. You can use commutative property, and you can say that that's equal to, you can just flip the order. Negative 10 plus 18 is the same as 18 plus negative 10, if you think about it, because you're just adding them. But then adding a negative just becomes subtraction. So you just end up with 8. So that's how it works. So Madeline, you asked the question, does that help for addition subtraction? Or if not, do you want to give me an addition or subtraction problem that I can work out on the board and kind of show you? And then after we get that, we'll go to multiplication and division. Or are you good? Okay, you indicated you're good on addition and subtraction. Now, let's look at multiplication division. Here's going to be the guiding principle behind it. Whether, boy, I can't spell today. Whether you're doing multiplication or division, it's all about the signs. So no matter what you're doing, if you multiply or divide two numbers that have the same sign, either they're both positive or they're both negative, you end up with a positive. No matter what. So if I do 3 times 4, they're both positive numbers. So we know the solution will come out positive, and we can just call it. I multiply two negative numbers, negative 12 times negative 4. They're both negative. It's almost like if they're both positive, it's obvious they'll come out positive. But if they're both negative, you can almost think of it as like the two negative signs cancel each other out, like double negatives, things like that. So it's going to come out positive, and it'll be 48. And of course, when something's positive, you don't need to put a sign in front. I could say positive 48 and put the plus sign there, but it is unnecessary. For division, Tom Clancy's The Division or otherwise, again, if they're both positive, so if you had 18 divided by 9, both the 18 and the 9 are positive, so your response will be positive, positive 2. But even if you did negative 36 divided by negative 6, come on, let's make it look a little better than that. They're both negative numbers to start with, so you're going to end up with a positive outcome from that. And then you need to know, okay, I already know it's going to be positive, and then 36 divided by 6 is just 6. So that's if you have both positives or both negatives when you're going into it. If you don't, if you have mixed signs, different signs, then the solution is going to come out negative. It's going to come out to be negative. So if you are multiplying or dividing, oh my goodness. If you're multiplying or dividing a positive with a negative, the solution is going to be negative. It's like saying, well, I've got a positive with a negative, but the negative actually wins out, mathematically speaking. So if you have 3 times negative 4, the solution will be, once you know the sign, then just do 3 times 4. So the solution is negative 12. If you had 16 times negative 2, let's make it more interesting than that. Let's make it negative 16 times positive 2. And you could put the negative 16 in parentheses, but you don't actually have to. And I even could have not put up here, I could have left this negative 4 without a parentheses, but look what happens. I get 3 times, you could almost accidentally ignore the dot that says multiplying, and you'll think it's 3 minus 4, which it's not. So that's why I like to put parentheses in that case. And it's not necessary in this case, because now you can see the negative can only be talking about negative 16, and then you can still see the dot. So it's just kind of your fancy you'll know the answer needs to be negative. And then 16 times 2, you can do old school multiplication, but you should see that it's 32. So it ends up being negative 32. Division is similar process. 21 divided by negative 7. Well, I know that's got to be negative because they're mixed, and then you can know that 21 divided by 7 is normally 3. So 21 divided by negative 7 is negative 3. And it makes sense because you would do negative 7 times negative 3, which would give you positive 21. So division is just a reformation of multiplication. And then, of course, you could do negative 42 divided by positive 14. Maybe you know what that is. You know it'll have to be negative. And then that one also turns out to be negative 3, just by coinkydink. So does that make sense, Madeline? Or is there another one you want me to try out on that? I'm more than happy to. Very good. So she understands it. Very good. Very good. And that's a nice opportunity for me to take a bite of spaghetti. If you guys want to know, I have a really special kind of family secret way that I make spaghetti. What I do is at the grocery store, wherever you get your supplies, your groceries, I get a box of spaghetti and I get a jar of tomato sauce and I heat up the tomato sauce or the spaghetti sauce, whatever you're using, and I boil the spaghetti noodles, and then I drain the noodles, and then I put the two together. I know, right? That's shocking. It's insane. If possible, could you go over adding and subtracting square roots? Absolutely. That is a good question. Go over adding and subtracting square roots. I work at Olive Garden, so thanks for the tip. You're more than welcome. I hope that the chefs at Olive Garden will use my secret way of making spaghetti. So adding, subtracting irrationals, which is a fancy way. Remember, that's my same recipe. You don't say. Adding and subtracting irrationals. Remember, when you take the square root of a number that is not already a perfect square. So if I took the square root of like 17, that's not pretty. The square root of 16 is pretty. Square root of 16 is 4 because 4 times itself, 4 times 4 is 16. The square root of 25 is pretty. The square root of 49 is pretty. But when you take the square root of a number like 17 or the square root of 28 or the square root of 95, it's not going to come out pretty. It's in fact going to be an irrational number. Irrational number. Meaning that when you express it as a decimal, it goes on forever and ever. It keeps going and going. It never terminates. And it also does not just repeat a pattern. It's seemingly random. The numbers just keep going in no particular pattern. So what we can do then is we can add or subtract irrationals. Now you have to think of it like it's like terms. You can't just add x squared with a 7y because those don't have the same variable setup. They're not like terms. So when you're doing it with irrationals, think about them as like terms. And when you do that, let's say you have 4 square roots of 3 minus 6 square roots of 3. Don't let it horribly bog you down. The object is the square root of 3 business here. This thing. Now the square root of 3 is not pretty. The square root of 3 is not pretty because 3 itself is not a perfect square. You don't believe me? Go put it in a calculator. Go do square root of 3 in a calculator, and you're going to get 1 point something, and the numbers are ugly. 1 point blah, 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 blah. So it's not going to come out pretty. So we know this will work. If I was trying to do the square root of 25 in here, well, I'll just quickly convert that to just 5. The square root's gone, and now you're not talking about irrationals. But since square root of 3 is not pretty, we can do this. Now, think about it in like terms. Imagine if you just had 4 x's, all of whom live in Texas, and you were subtracting 6 x's from that. When you combine the like terms, you would verify that they're like terms by looking at their variable setup. Oh, they're both just x squared, so they're like terms. Or excuse me, they're both just x, so they're like terms. Or if I did x squareds on both of them, they're still like terms. So you think about it, the numbers in front, the coefficients, are telling you how much of that object you have. So I have 4 of this x squared object minus 6 of this x squared object. 4 minus 6 is -2, so that means I have -2 of that object. Or it could have been a y. I could have put a y here and a y here. But here's the problem. If I put a y here, but I leave this one as x squared, that business doesn't happen. This is as simple as you can write that algebraic expression. You can't get any simpler than that. But, restored. So let that be your guiding principle here. Here you have 4 square roots of 3 minus 6 square roots of 3. So I can just say I have 4 minus 6 is -2 of that object. And that's the answer, -2 square roots of 3. The negative sign is not on the inside with the square root. Remember, that creates problems that we're not dealing with just at the moment. But yeah, I can just say it's -2 square roots of 3. Well, what if I mixed it up a little bit and I did 4 square roots of 5 minus 6 square roots of 3? You look at that and you go, what is it? Is it? They're not like terms, because the square root of 5 is not the same as the square root of 3. This object, the square root of 5, is different from this object, the square root of 3. So that one's done. It's done. There's no simplifying that. It just, you can't do it. Now that's still a number. You can still literally do that subtraction. You'd want a calculator in that case or something. This would still come out to some number, but this is as simple as you could express it in exact terms without having to round. But knowing that in mind, that you need them to kind of be like terms, they can manipulate you. They can manipulate you and try to trip you up. What if you had -5 square roots of 6 plus 2 square roots of, let me think of an interesting one, plus 2 square roots of, I'm trying to get an interesting one. How about just 24? Now you guys in the text box, as I secretly take a bite of spaghetti, you guys in the text box, let me know, are those like terms, yes or no? And if not, why not? Okay, so looking at those, you're tempted to say they're not like terms because the objects inside the square root basically have to be the same. And so at the initial moment, it looks like they're not like terms. But Xavier has it. Yes, they can be, because you can actually break the 24 down. Here's what you can do. Now the 24, you could write 24 as 8 times 3. And now here's what we're going to do. That's going to be 2 times the square root of 8 times 3 inside the same square root house. And then you could split off the square roots. Let me just write with my finger. Here we go. You could do that. These are all protected mathematical operations. All I did was rewrite the 24 as 8 times 3. I can split them off into the 2 separate square roots through multiplication. Remember, that was a rule we went over specifically in class. But is square root of 8, is that a perfect square? Is that pretty? No, it's not. Square root of 3 is also not going to be pretty. So we don't want to write it like that. Here's a smarter way to do it. If we can rewrite it so that the factorization we use has a perfect square coming out of it. So, how about 4 times 6? Ooh, everyone say, ooh. Then we can rewrite it like this. Oh, did someone say ooh in the chat box? We got some oohs. We do got some oohs. X is an ooze. Very good. Ivan Ooze, the villain of the first Power Rangers movie. Yes, we can do it that way. And so we can rewrite it like square root of 4 times square root of 6. Remember, it could have been in the same square root house, but we split them up. And now the square root of 4 does become something a little bit different. Square root of 4 is just 2. Square root of 6, though, there's nothing you can do about it. It is what it is. But square root of 4 can be written as 2. And now that becomes 4 square roots of 6. So this 2 square roots of 24 up here, all the way down here, breaks down into 4 square roots of 6. Ooh, and that's extra wonderful because we just bring this back down to where it was, negative 5 square roots of 6 plus 4 square roots of 6. Negative 5 plus 4 is negative 1, so you can say it's negative 1 square roots of 6. And then technically, whenever a 1 is a coefficient, you don't actually need it. So you can just say that's negative square root of 6, and it's automatically negative 1 square roots of 6. So they might trick you. They might try to trick you. They might even do something like this. Let me do a different one. They might even try to do something like this, where they put a 54 in there. But then you can know that 54 is just 9 times 6. And so then the 9 is a perfect square. It comes out, and then you'll still have square roots of 6 left over so that they're like terms. So I hate to say it, math shouldn't be all about just trying to trip you up. But math's all about just trying to trip you up. Let's just call it like it is, right? That's not true, but they do want you. They want to kind of test you over. How many different ways can you see these same problems? Of course, I write your exams, so we'll see what I see. All right. What else you guys got for me? You can pull up a homework problem from MyLabs Plus. I'll work it. You can pull up. You can ask about a specific concept. I can go over it. These are all good questions. I'll give you about a minute, and otherwise, I'll write out something I think is important for y'all to know. So I'll give y'all about a minute to give me something. You can go look around, root around. Okay, I got a request to do. Let me go pull it up real quick. I got a request to do section 5.5, number 9. So Let me go bring that bad boy up. Lock me out of MyLabs Plus. That's rude. Let me go get on back in here. Ah, this is great. So actually, Madeline, this was one that I wanted to cover anyways. So this is perfect. This is a question over different types of numbers. And the different types of numbers are super interesting to me. I just love the way they flow. Let's go over that real quick. So different types or different classifications of numbers. A specific number can actually fall into multiple categories. It's not just necessarily one. First things first, you have what's called the natural numbers. They're written with this weird N, and it's not quite an N. It does like it has a little extra on it. N for natural. And the natural numbers are actually the set of all the positive whole numbers. So this would be the set 1, 2, 3, 4, 5, 6, dot, dot, dot. Of course, it keeps going on forever and ever and ever. And we've gone over this numerous times, so I won't dilly-dally. What we call the integers, they use a special Z. The Z stands for Zahlen, which is the German word for number, and it has this kind of weird looking symbol here. Something like that, a weird Z. Almost like it's like 3D, man. All right. Now the integers include all the natural numbers. So the integers include 1, 2, 3, 4. And that goes on forever. The integers also include 0, and they also include all the negative versions of those same natural numbers. So -3, -4, -5. But integers are still, they're almost like whole numbers, but they can be positive, negative, or 0. You can't go in between. You can't do 5.5. This creates an interesting relationship immediately. Any number you give me that's natural is automatically also an integer. But the other way is not true. I can give you an integer and it might be natural, but there's other integers that are not natural. Now the next numbers we talk about are the rational numbers, and they use a fancy Q, and I'll use shapes here. They use a fancy Q that kind of looks like this. The Q is actually for quotient. A quotient is one number divided by another. So the rational numbers, these are all numbers that can be expressed as one integer divided by another. Of course, you can't divide by 0. So because 0 is an integer, but we have to throw it out and say we're not going to divide by 0. You can have 0 on top. You should be thinking about fractions on this one. Your fractions, your traditional fractions, are going to be rational. But also, remember, we argued that a whole number can be written as a fraction. The number 4 can be written as 4 over 1. So it fits the definition here. 4 can also be written as 8 over 2 if you wanted to. So actually, all numbers that are natural are also integer and therefore also rational. But then the rational numbers include some things that are not integers, like 3 over 2, which simplifies to 1.5. 3 over 2 is rational, but it's not going to be an integer and it's not going to be natural, clearly. But here's actually secretly and this is a secret. I want everyone to themselves to go, pss, 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 it's a secret. You don't actually have to do that, but you should. Secret. All rational numbers, when written in decimal form, not fractional form, all rational numbers written in decimal form either terminate, meaning the decimal just stops, or if they go on forever, they do so via a repeating pattern. So 2/3. 2/3 is equal to 0.6666666, and the sixes go on forever. It goes on forever, but it's a repeating pattern, so it's rational. The number 3/4, when you write it as a decimal, becomes 0.75. And then it stops, it terminates. So that's still rational. So this brings us into our last major set that we're going to be super curious about at the moment, the irrational numbers. These are going to be, it doesn't have a special symbol. These are going to be numbers that go on forever with no repeating pattern, that are not rational. They go on forever with no pattern. And then all the numbers of interest are going to be called the real numbers. All our numbers of interest, rational or irrational, all together are called real numbers. Real numbers use this special symbol. It's like an R, but with a little extra on it. We already used that symbol earlier today. We can draw a nice little picture. Here's a picture of the real numbers. Ooh, it's a nice box. Hello, box. And we can split the real numbers into two parts. Now, they're not the same size. The irrational numbers are actually much larger, but that's okay. We can split them into the rational numbers with the weird Q. And then the irrational numbers. There's no overlap, which is why the box is split apart. Anything in the irrational box does not fit in the rational box. But then inside the rational box, you can also have the integers. So we'll use the fancy Z for integer. So all integers are rational because if you're in this box, if I pick you, you're inside the integer box, you're also inside the rational box, and then you're definitely inside the overall real number box. No, you give me that. So these are the real numbers. And then even furthermore, inside the integer box is the natural number box. And that's not very good. Let's draw that a little bit better. Whatever. The natural number box. So if you're a number that's natural, if you're a 3, right here, positive 3, you're in the natural number box. You're also in the integer box, so you're also an integer. You're also in the rational number box, so you're also rational. You're also in the real number box, so you're also real. Some examples of the irrational numbers. The classic example is American Pi. Pi. Remember, pi is the ratio of a circle's circumference to its diameter. Pi is about 3.14. It's roughly 3.14159. It goes on forever, though. Your calculator has to stop at some point. So if you'll put pi in your calculator, it's not actually terminating, but your calculator can't show you an infinite number of digits. It's impossible. It repeats on and on and on and on. but it does not do it by a pattern. The other major example is basically any square root number. Anytime you take the square root of a number that is not of a perfect square. We already talked about that. So if you took the square root of 7, 7's not a perfect square. It's between 4 and 9, which are perfect squares. So 7, the square root of 7 is going to look ugly. The square root of 46 is going to look ugly. Square root of 49, though, will look pretty. So square root of 49 doesn't belong in this box. So don't assume just because you see a square root, you're talking about irrational numbers. So now, let me actually get to your problem, Madeline, that you wanted me to work. Let me bring it up. Cool. Do you see what I see? Mr. Gunther, please don't ever sing again. Deal. I'll make that deal with you guys. Any day of the week there, Pilgrim. Let's look at each of these numbers. They got 1.3, 4/5, square root of 25.5. Let's categorize them. And some of them are going to have multiple categories. So let's start with, I'll annotate. Let's start with 1.3. 1.3. Let's get that a little bit better. Actually, I'll just draw a box around it. The number 1.3, it's not natural. No. That's bad. It's not natural. It's not a whole number. Remember, we're not going to worry about whole numbers. This problem might, so just say a whole number is all integers greater than or equal to 0. So 0, 1, 2, 3, 4, 5. That's a stupid, I don't know why they teach that. Whole numbers, I rebuke you. It's certainly not an integer because 1.3 is between 1 and 2. An integer would have to be the 1 or the 2. But it is rational. Yeah, it's rational. Because either you're already writing it as a fraction, a ratio of two integers, or if you write it in decimal form, it terminates in this case, automatically making it rational. And so because it's rational, it can't be irrational. So we don't worry about that. But finally, it's going to be a real number. In fact, all of these are going to be real numbers. The only times you deal with real numbers that are not real is if you deal with, at least in our case, if you ever talk about the digit I lowercase I, it's called the complex digit or complex coefficient. We're not going to deal with it. So 1.3 is rational. It's also real. Those are the two categories it fits in. Hint and a wink, and you might just have some problems on the exam, this first exam here, that are just going to simply give you a number and say check all that apply, or give me all the labels. So you go down, you just check all the labels that apply to that number. Hint and a wink. That's exactly the kind of problem you just might see on the exam. So 1.3 is rational, it's real. Let's see if we can go through the rest of these fairly quick. 4/5. 4/5 can't be simplified to like 1 or 2. 4/5 is about 0.8. You don't believe me? Go do 5, divide 5 into 4. You'll get 0.8. So then it's obviously not natural. It's not whole. It's not an integer. It is rational, though. And it's especially clear that it's rational because it's written as a fraction, one integer divided by another. Can't be irrational, but it can be real. In fact, these are all real. So 4/5 is both rational and real. What else do we got? Square root of 25. Don't let that confuse you, Pilgrim. What is the square root of 25? Someone tell me in the chat box. What's the square root of 25? 5 is correct. So don't let that throw you off. That's just the number 5. So really what you can tell yourself is, oh, okay, let's pretend like we were dealing with a 5 here. And once you do that, it'll become clear. Oh, okay, so 5, 5, 5. Well, shoot, 5's natural. It's a positive whole number. It's also a whole number according to their definition. It's also an integer because if it's natural, it's automatically an integer. It's also rational because all integers are automatically rational. It can't be irrational, though, because we've already identified that it's rational. Irrational, literally, the IR at the beginning means opposite of rational or not rational. So you can't ever have a number which is both rational and irrational. It doesn't make sense. And then finally, these are all just real numbers by default. Okay, 0.5, we'll skip it. It's basically going to be the same thing as 1.3. -1 might be interesting. It's not natural because natural has to be positive whole numbers. It's not whole because whole numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, blah, blah, blah. It's just the natural numbers with 0 included. But -1 is certainly not among them. But it is an integer. And since it's an integer, it's automatically rational. And since it's rational, it's automatically real. Or really, any of these are real. Square root of 5. Is the square root of 5 a nice, pretty square root? You guys tell me in the text box. Square root of 5, is that going to be pretty? No, Xavier, you are correct. Madeline, you are correct. Square root of 5 is not going to be pretty because, Nicole, you're correct. Because the pretty squares, the perfect squares are 1, 4, 9, 16, 25, 36, 49, and so on. Just think about 1 squared, 2 squared, 3 squared. So square root of 5 is not going to be pretty. So let's think. It won't be natural. You don't believe me? Well, it's just by definition. It won't be whole. It won't be an integer. It won't be rational either. It's a classic case of an irrational number, but no matter what, that's still a real number. What else? We've got negative pi. Now, if pi is irrational, regular old pi is irrational, do you think slapping a negative sign in front of it is going to change that problem where it goes on forever with no repeating pattern? What do you guys think? You think putting a negative sign suddenly changes its nature when you look at its decimal expansion? Yeah, I'm going to say no. It's still 3.14159, blah, 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 blah. 3.14159, it'll go on forever with no pattern. Putting a negative sign, okay, it's just negative 3.14159, blah, 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 blah. It still has the same problem as regular old pi. So it's still going to be irrational. And it's still going to be a real number. And then finally, 0. 0 is not natural because it has to be strictly positive. But because they call the numbers whole numbers, which again, this is like no mathematician talks about whole numbers seriously because it's like, who cares? In fact, some textbooks and some mathematicians call the natural numbers, they include 0 in their set of natural numbers. So it can create a little confusion among different like mathematicians and whatnot. But it's still an integer, which means it's also rational and it's also real. This is a good kind of exam problem. It's exactly a kind of problem. It may not look exactly like this, but there's a similar idea. Good exam problem here. So that was a good question to ask. Okay, I think we have time for about one more either question or how many of you guys would like me to just go look at the exam I've written and go see something that makes sense to go over real quick? You guys want that? Yeah. I didn't think anyone would say no to that little proposition. And that'll be the last thing we look at. Remember, the exam is found in Canvas. It's found in Canvas, not MyLabs Plus. It will use the Respondus Monitor lockdown browser system. Let's go take a gander. Do you guys remember what a prime number is? Does anyone want me to kind of go over again what a prime number is? I'm more than happy to. Prime number versus a composite number. A composite number. Just remember a composite number versus a prime number. A prime number, we're clearly just talking about positive integers like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're not talking about negative numbers. You can, but we're not going to in this class. A negative number won't get the prime label. And a weird fractional number also won't get the prime label. But a number is prime if the only things that divide cleanly into it are 1 and itself. So think of the number 2. The only two things you can multiply, the only integers you can multiply to get 2 are just 1 and 2. So 2 is a prime number. 3 has that same problem. 4 does not have that problem because 4 can be written as 1 times 4, but it can also be written as 2 times 2. So 4 is not prime, it's composite. 5 is prime. 6 is not prime, it's composite. So composite just means not prime. So I think we get the idea of a prime number versus a composite number. The last thing we'll look at, we'll remember what exponents do. Gonna give it to you. You may not get that joke. Some of you might be a little too young for that joke. X gonna give it to you is a rap song. When I was in like middle school, X gonna give it. Nah. You know what? Hold on. Let's just get rid of that joke. Yeah. I reference that all the time. Well, Xavier, you are a true king. Not that you're not a king if you don't know the joke. It's just a stupid song. Exponents. So an exponent, let's say you have 2 to the 4th power, nice and big. What that's telling you, it's not 2 times 4. Don't make that mistake. It's telling you to take 2 and multiply it to itself however many times. So technically you're only doing 3 multiplications if you, whoops, oh, I said 3 out loud and I wrote it. You're only doing 3 physical multiplications, but again, it shows up 4 total times. So 2 times 2 is 4, times 2 again is 8, times 2 again is 16. Where they can really get you though, if they say -2, say, to the 4th power, what they mean by that is take the -2 and multiply it to itself. And it's especially true because the -2 is in parentheses. The whole negative with it. So as you can see, that's going to come out to positive 16 again, because these negatives cancel, time another negative, but then times yet another negative makes it positive again. So be careful, because here's where they're going to try and get you. And by they, I mean me, because I'm writing your exam. This is a good one to get you. Notice the negative sign is not in the parentheses. So here's what's actually going on. According to order of operations, I actually do the 2 to the 4th first. Remember, because exponents take place first. And technically, you could say putting a negative sign is like multiplying by -1. So the exponent takes place before multiplication. So actually what that means is do the negative, but actually do the 2 times 2 times 2 times 2. Do the exponent first, and then just slap a negative sign onto it. So that comes out to -16. So that can be really confusing, because if I would have just put it in parentheses, that would have been actually positive 16. But I don't put it in parentheses, it's negative. But that's only because it's a 4th power. 4 is an even number. What you're not seeing is that -2, if I did it to an odd power of 3, either way, the final answer is going to come out negative because it's an odd power. So that would come out to -8 because there's like an odd man out making the whole thing negative. But even if I drop the parentheses, it just so happens it's the same dilemma. Only instead of 3 negative signs, you only have 1 negative sign, but that still comes out to -8. So don't let that trip you up. Okay, I think that's going to do for today. Take your exam. You can take it anytime Thursday, but I would just take it during our class time. But you can do it literally starting at 12:05 a.m. on Thursday all the way, and then you have to have it in for 11:55 p.m. Thursday. Anything special you need to do to prepare for the exam? No, I think, remember, you got to take your scratch work while you do the exam. You can't have your book, notes, or calculator, anything like that, out while you're taking the exam. Other than that, if you're doing okay on the homework, if the stuff's making sense, if this review made sense for you today, the exam's really straightforward. There's some multiple choice, there's some there's some matching. There's just type in a numerical answer. So it's all pretty straightforward overall. Remember, I'm going to grade your work. So if you submit your exam and you're like, I'm pretty sure I got these right, why did it grade it wrong? It might have just been an input error, or you put an extra space or something where you shouldn't have. So that way I will go into your work and I'll say, okay, you clearly got it right on paper. I'm going to go in and give you back that credit. So that's kind of the whole reasoning behind taking your work and submitting pictures of it. Remember, you got to submit pictures of your work within 30 minutes of finishing your exam. I can see the times. You'll see that place where you submit it in the same place that you're finding the exam, the same module in Canvas. So it's really straightforward. You'll just submit the pictures of your work. Make sure you can double check after you submit. Go back in and look at it. Make sure you didn't send me some weird file. Make sure you sent me image files, and make sure you sent me all of them. So good luck on your exam on Thursday. If you have any questions, shoot me an email or a Canvas message at any time. And you guys have a great day.